Okay, for people joining this live stream, sorry, we're starting a bit late again. This is about array operations, and it's a little bit of a mind-bending subject. And Etienne has provided something which he is initially claiming is going to help us unscramble our understanding here. So let's start off here. Okay, so we are talking about different kinds of things that can happen here. Okay. Okay, so this is array, that first thing, I to a rule J, that's already supported, right?
Yeah.
And that swaps two levels.
Yeah. This is
Can I ask a question? And this is maybe more of a Jose question. Tensor diagrams with creatures with legs, you know, like Penrose tensor diagram-y type things. Are those useful in understanding what's going on here?
I'm not sure.
Okay. Could we invent, question, I mean, I don't know whether it's useful, but could we invent a diagrammatic, in a sense, diagrammatic notation for some of these operations?
I think
like,
I would
for example,
start.
Go ahead.
Sorry, I think I would start by trying to express the notations with indices. That might help, rather than numbers.
Right. But I mean, then things like, you know, there's various operations, like there's taking a trace, or, you know, which is basically gluing two legs together. There's transposing, which is basically exchanging two legs. There's, yeah, I mean, we should write this out. I think we should write it out in terms of indices. We've got some operations here, like flattening, which is not an operation you normally do with tensors. Am I correct?
Right. So the fundamental operations with tensors are tensor product, tensor contraction, and transposition. And those are easily expressible with indices, but flattening is not. Anything related to array reshaping is not that easy with indices.
Well, but that operation, array reshaping, I mean, curiously, in the physics project, we have some examples where we basically are doing array reshaping, which turn into these weird space-filling curves in branch-hill space and all kinds of weird stuff like this. But it is basically array reshape. It is essentially flattening.
There's another point to make, which is that if you think about what something like MapThread is doing, and I think MapThread is the tip of a vast iceberg of flexibility that we haven't figured out how to index properly, right? If you think about what MapThread is doing, it is very similar to a tensor contraction in that, you know, you've got two things with legs, and you're saying, I'm going to match the first leg of this guy and the first leg of that guy and walk over them simultaneously. Yes. So I think there is maybe a connection with tensor diagrams, but it might be quite a sophisticated algebra that we haven't yet worked out.
So I do have
you can also think of MapThread though as, go ahead.
So I was going to say that I do have a way of expressing threading operations via indices. I haven't thought about legs. I mean, type of.
What is it? Yeah, I mean.
Let me look for it. I can send you something.
Okay. All right, but let's, okay. I just wanted to raise that because I think it might be useful. And I mean, Tally is making the point that MapThread, arguably, any tensor operation, I mean, MapThread is doing one particular n tensors, you know, contraction operation. And what I think Tally might, go ahead.
If you scroll down a little bit, I put something about MapThread, just in explanation in terms of dimensions. That's kind of it was helping me understanding all these things. So this, if you say
like
MapThread,
these colored pictures are quite nice.
Thanks. So if you say level 2, what it does is that it always takes the first level. So MapThread, I mean, at least in this current specification, always take the first level and then put it somewhere. So if you say level 2, it will actually put it level 2 plus 1. And then it applies F starting from this level at this level. effectively. So on the arrays that are at this level.
Right. So, I mean,
I guess another thing is you can kind of just think about it as it's collapsing the tensor in some dimension, right? It's like saying,
Yes.
right.
So in fact, you can say a little bit more precisely. You can say, so go back to my legs business. You can say, you've got a list of these objects. They've all individually got legs. And when you say comma n, you're saying I'm going to take the nth leg of each of these objects and feed them all simultaneously into a function that will combine all of those guys, produce one result, and that eliminates the leg from all of them. So the result will have the resulting expression that comes out of MapThread will have, I'm not quite sure if it's, what legs will it have?
well, I think what you're describing there, so let's talk about how tensors work. And, in standard tensors, you simply apply an operation like summation to covariant, contravariant indices, right? So what we're doing here is we're generalizing that, and we're saying you can have an n-array operation to combine indices, to combine elements, right? So that's the first generalization. And there may be other generalizations, but that right there is going to change tensor calculus, so to speak. Yeah, I mean, it's clear there's a calculus of what's going on here. And did Jose, did you find your indices analysis, or?
I'm about to send it to you.
Okay. But let's go back. Let me just save this file so that I put it in a reasonable place. Let's see, let's call this. Okay, all right, let's go from the top of Etienne's thing now.
Yeah, this transpose was just a side thing because it was making it easier to express ArrayReduce and also this level applied that you were talking about last time.
Okay, this is, oh boy, this is.
No, this is the whole notebook, but the only thing we are interested here is this Lambda notation. So this is the algebra I invented to do these things. So this is a notation, this is an algebra that has the global idea of contraction and can implement MapThread, outer, inner, all these functions can be expressed in these notations.
So I see, so your Lambda here is a generalized tensor, is an n index contraction, is that right?
Exactly.
Where the combiner function is G.
Exactly. And G, yeah, we could have list, sum, table, etc.
This is a nice notation.
Right. And then if you go to, for example, contraction of several arrays and go to MapThread and Lambda notation, so that would be the expression in this language.
Okay, so hold on. So you're saying nth map thread here is
Lambda, when Lambda doesn't have a G on top, means list.
Okay.
So that's kind of like a transpose, I guess, if there's no G on top.
Yes, if you want. Transpose would be reordering the indices. So
no, what this is saying, where does it insert them? It takes these indices, this Lambda takes these indices, and where does it put them?
So this means we are going to have a number of indices of list levels around the whole thing. So that's going to be an array of that depth. Those are the indices of this resulting array. And the elements are going to be Fs of arrays.
No, I understand that, but in this pure Lambda here, right, that takes these, as I understand it, what it's doing is it's saying, take a trace over these indices here, feed them into, I'm confused about what this is returning.
So it's returning an array of those n levels, which are which have indices p1, pn. Then each of them at that level, there are elements F of arrays, and then the traces are in the repeated indices, which are the P1 PNs.
I'm slightly confused, but my gosh, what is this?
These are other notions of contractions and array operations that I had explored with Roger. And this is the conversion of these things we are discussing into graphs.
This is conversion by, these are the tensor indices or something, is that right?
We are working with tensors for indices, and those are the contractions, yes.
So this is a representation. So a ternary, so something, there's an in degree and an out degree or not? Is it like you take n indices and you're combining them? And should I think of it in the following way, that this, that there's like an f at every node here, and that you're taking certain edges here that are incoming edges, combining them with the f, and then sending them out to some outgoing edges? Is that right, or is that the wrong picture?
So there are two types of edges here. And I think in some of the diagrams I use different styles. So some are the edges forming the tensor, and then there are other edges, exactly here, edges contracting the various indices of the tensor. So here we have two tensors, which are the two black boxes, and they are contracted in pairs, right?
Yes.
And so we see still two free levels or slots or indices, which are not contracted in the first diagram.
I'm still not completely landed on what's going on here. I mean, I think a question is this really a story of you know, okay, let's go back maybe to Etienne's discussion here and see what, I mean, okay, so Etienne, we were talking about transpose. What is that new notation here? I goes to J, or is that an existing notation?
No, it's not an existing thing, but it's something I thought could be useful. So it's taking level I, removing it basically, I mean, or axis I don't know how to say it, and then put it in position J. So it's a way to define a permutation cycle in a way, which is useful to express ArrayReduce and yeah.
Well, if I can just endorse this, so this is actually, it's very useful when you know that you have something at a certain level and you want it at a different level, because otherwise you just you're forced to kind of doing the mental calculation of what the permutation is that does that. And that's just, I mean, you can obviously work out the permutation that does that, but why force people to do that? It's easier for them to think, well, something's at level 3, but it should be at level 2, and then just go 3 arrow 2.
Why is that different from swapping those two levels, or am I totally confused?
Because the order doesn't change. So check this example. The dimension were 3, 4, 5, 6. And I want the 3 to be at level 4, but 6, I don't want it to be at level 1. I want it to stay next to level 5.
I see.
It shifts them through each other. So it keeps bumping the 3 to the right, to the right, to the right. And that turns out to be actually much more, yeah?
I wouldn't say that this doesn't change anything else. It's changing all the indices, actually.
Right, so what this is doing is, this is replace part, which is saying replace, no, this is not replace part. This is the inverse, where it's saying take level 1 and put it at position 4. No, it's I mean,
it really is the same thing. It really is the same thing as the swap two levels, except that it's just what do you do with the, you know, it's basically, it's just what do you do with the one that was in position 4 now that you've moved 1 to 4? And so this is just, you shift everything over as opposed to
swapping it.
Yeah.
It's cyclic permutation.
Why
all of them.
Why isn't that second argument to transpose on the implementation just rotate right of range of depth?
Well, maybe if you're moving an indice to the left, then maybe it has to be a bit different.
That's probably better implementation. I did the one that, I just wrote that before.
Okay.
Yeah.
That's an interesting idea with
I inserted it and then inverse permutation.
Right. So in general, okay, if I remember, transpose takes a permutation as its second argument, right? You can specify a permutation as its second argument.
Correct.
But so one thing we could also imagine is that whatever specification of permutations there are, like a list of cycles and things like that, we should be able to give that permutation spec as the second argument to transpose.
So in other words, the syntax 2 arrow 5 means cyclically permute 2, 3, 4, 5.
That's what I think, yes.
That works already. So you can put cycles in the second argument of transpose.
Oh, it already works?
Yes, with cycles, not with lists of cycles. I don't know what that would mean.
Can we understand what that might mean? So a single cycle, okay, it doesn't seem to document this. Oh, or cycles, there we go, MN. Okay, I think it'd be worth thinking through. Go ahead.
Yeah, I don't think it is quite a cyclic permutation, because if you think what 1 goes to 4 means is like, or 3 goes to 6. It means take the 3, shift it over 1, swap it with neighbors until it ends up at level 6. It's not quite a cyclic.
It's a bit of a span. It's a bit of a range, cycle range, except that.
Oh, it's a rotate left. It's a rotate left, not a rotate right. So
exactly.
You take that whole 3, 4, 5, 6, and then you rotate left, and you end up at 4, 5, 6, 3.
Okay, so we should be able to compile 1 arrow 4 to some cycle specification.
For sure.
Yes, but it's going to be difficult to remember which direction it goes. The good thing of the two-way rules is that it's symmetric.
Oh, look at this.
It's intuitive to me, but yeah.
Pointing out that he's written this function repository item about tensor diagrams. What the heck is this doing now? Interesting. Oh my. Well, this clearly should be looked at.
Yeah, thank you.
This is kind of the inverse operation at some level, though.
Which is the inverse operation?
Well, at least my understanding of what this is doing is it's, or maybe not actually. I guess maybe it's using interpretation boxes, but I guess what it looks like what it's doing is you give it an existing array operation, and then it shows you what it looks like in tensor notation.
Which would be useful to us in our attempt to understand what's going on here, I suspect.
Sure.
Right. Good. Very nice.
What I can say is that the arrow syntax that we're proposing there, I disagree with Jose. I think it's very natural to interpret I goes to j in one and only one way, which is what was level I becomes level j. And there's only one way to shift them over that makes any sense, because one of them is local and one of them is not local. One of them, each thing moves up one level, the others that get scrambled in a weird way. And we use this all the time in the neural.
Go ahead.
Sorry to interrupt. Yeah.
Tally, you were saying.
4 goes to 1.
Yeah. Tally, you were about to say something about neural nets.
Yeah, we just use it all the time in neural networks. So, like, again, this is not a theoretical exercise. It's too hard to express common array permutations and acrobatics. And the place where we have a lot of experience with that is in neural networks. They're just very rich in linear algebra stuff and array operations. So when we say something like, this is a useful operation, like, trust us, like it's what we've been doing for years now. It is worth having some kind of short syntax for that concept.
Explain.
Anyway, that's just a
big
meta
picture.
point.
Okay, Tally, big picture. You got a neural net and it's a deeply nested array. Explain sort of the big picture of why you're doing array gymnastics as you connect those deeply nested arrays together. What's kind of the way to think about this?
I think the way to think about it is that you are kind of arranging various axes to be at the positions they need to be, so that a particular operation that you have available as a layer does the thing that you want it to do.
I see. And then puts things back out again. So in other words, you say you have a layer and it's expecting a pair of levels, and now you have to connect that to the right pair of incoming levels. And maybe does the layer often take in a tensor of rank n and put out a tensor of rank m, or how does that work?
Well, it's usually some are, yeah. So
ahead.
Often layers will do things like there'll be one privileged axis, which is, say, often the first axis or the last axis, and then the other axes are just ignored, right? And so I have a very strong suspicion that, and this is not just a suspicion, people have written about this, and I think, their arguments are worth looking at, that the current way that people do this sort of stuff, which is the sort of acrobatics of getting axes to the right point for various operations to do their thing, is going to very rapidly fall out of fashion when better ways are designed. And one of those is naming the axes, because as soon as you name the axes, you don't have to transpose them around. You just say, let me use an analogy. In the beginning of programming, we had registers, and you just had assembly language, and you could load your variables or memory locations into the registers, and then you'd have the operations that would act on those registers. And it was a nightmare of sort of like swapping things into the right registers for the instructions that you had available to you. And you didn't name them, and you didn't, you'd have to like reason about at this point in the program, what is register 3 containing? It's very hard to read that kind of stuff. And variables just revolutionized. Like no one went back to using, numbered.
Which brings us again back to the question of named levels, which we don't have, right? Because so that would be the conversion between these two worlds. So in other words, we could imagine a thing where we said, named level, this is a bad syntax, but something like named levels of array, comma, A, B, X, Y. Okay, that could represent, not a good notation, but that could represent an object which is choosing to call its nth level, B or something.
Yeah, exactly.
And then what we could do, go ahead.
Well, that's one syntax, I agree. So that's where you have names for all of the levels in order. Level 1 is A, level 2 is B. You might also have the situation where sometimes you have a name for just one level, like a sparse naming.
No, that's fine. So you say 2 arrow Y or something. But then the question is, then the idea would be, if you had a named level object, you could do something like, but then it's not completely clear what you'd want to do. But then you could say something like transpose, and you don't have to know. You would say something like, A goes to X.
That would just be a renaming. There would be no need to actually manipulate the underlying array. So I agree that that's well defined, what you've written. Mm-hmm. But you see, the need for transposing largely goes away when you've got names for the levels, just like the need to swap registers goes away when you've got variable names.
I see.
Well, although there might be efficiency things internally when you might want to do that.
That is true.
It's unclear. It probably depends on what you're doing. Yeah.
Yeah.
Right.
Yeah. But you see, so in the grand future, which I think eventually will dawn on us, that'll be a compiler problem. The compiler will look at the program you've written and say, well, I know you're going to do this outer product at this point, and that's most efficiently done with dgem, with BLAS operations, if those two things are at the top, if it's row and then column and then whatever. And that's not something you'd ever worry about. But we're not there yet.
I agree. So it's basically register allocation versus, it's the analog for levels of register allocation.
Yes.
Right.
Yeah.
But
it's also maybe there's an analogy between lists and associations of this as well. Where it's the same kind of thing of you refer to it with a name instead of an index.
Yeah,
well,
that's
exactly.
True.
Right. But
so I think the story that we have from before, which was, you can think of associations as just taking lists and generalizing the parts to be not just integers, but other things. I think that story now carries over, except we're no longer talking about the elements of a list. We're talking about the axes of a multidimensional object.
Right, but the thing I don't understand is if you have something like ArrayReduce, and you've only named some of the levels, how is that operation well defined?
It will have to be all the levels named now.
No,
Well,
ArrayReduce.
what's wrong with it? I mean, if I'm array reducing over level X, and I know that level X, you like with associations, maybe you can kind of, I mean, you can. If one way of doing it is you can just say, well, level X is actually just, it's actually just,
level 7 or something.
Level 7, right? And then you just run it over level 7. I mean, I guess it is.
I think that's very
true.
well
It is
defined.
a little weird though, because it is like having an association where you don't have all the keys.
Yes.
Well, let me attach the semantics, because I think there's a very natural semantics for this exact case of ArrayReduce of only one names level, and you only have one named level, right? So remember what ArrayReduce does. It deletes the axis that you asked to reduce. Like whatever comes out will have one less axis, and the one that's missing is the one you asked it to remove. Now, normally when you have numbered indices, that's all a little bit confusing, because the numbers before and the numbers after have this sort of complicated relationship where some of them are the same and others are shifted over. But when you have named levels, and even if not all of them are named, whatever one you asked to delete by reducing, it's gone from the naming. And whatever's left over is left over. I think it's very
it's like key delete or something in an association.
Yes, and I think it's easier to reason about, because with associations, if you delete a key, all the other keys have the same meaning they had before. But with a list, if you delete an index, then some of the indices match, and others don't. The ones after the one you deleted no longer match up.
Right.
That's why it's actually easier to, it's just why it's easier to deal with named axes, because all of this kind of keeping track of allocations goes away.
Right. I mean, it reminds me of a weird thing in SMP. So in SMP, I had a combination of associations and lists. So there were symbolically indexed lists, and it did the crazy thing that when the list happened to have indices that were sequential integers, it would order them in the order of a dense list. That was insane. But this is
that's also the choice that JavaScript made. So I'm not sure. I mean, it is insane, but it's also a mistake that other people have made.
Oh, well, they only did it 30 years later or something, or whatever it was. Yeah. Okay.
Yeah.
That's interesting. I didn't know that. I didn't know anybody else had made that stupid mistake.
By the way, I mean, one other thing is, maybe one other way of thinking about having some unnamed levels is, if you had for example, if you had a named levels of an array, and the array is deeper than the number of sort of names you give, you can kind of think of it as a named levels array where the elements themselves are arrays.
Yes, exactly. So a very good example of that would be something like you have a bunch of matrices for different countries, right? That naturally shows up as a names levels object where it's got 3 axes, it's rank 3.
Mm-hmm.
But the first axis is country. Maybe that's an association axis. In fact, that's one thing to keep in mind here, is that we might want some of these axes to not just be integer axes that take integer values, but also keys.
Right. I mean, this is something I was going to say earlier, is that, more generally, this is something that sort of has been discussed certainly with like data set and things, but I don't think anything has actually been done, which is kind of association arrays, where you don't have to, where it's secretly some packed object instead of it the kind of horrible thing where, I have 10 million rows and every one of them is an association with the same key.
Okay, so to highlight this, okay, so data sets can be ragged. What we're basically talking about here is dense arrays, rectangular-ish arrays. Is that correct?
Yeah. Although
yes.
it's interesting how it can generalize to.
Well, I'm not sure
what do you do?
it.
Maybe you could have missings or something, which let you make it ragged, but yeah,
Right.
I think we should think about it as dense.
Raggedness with missing question mark. But right, I agree. So the question now is, if it's data sets, if data set always knew it was going to be rectangular, what else could it do? Right?
Well, I think it would fix a major deficiency with dataset, which is that, and this is really about the naming rather than other things, the naming of the axes, which is that, designing queries, you've got a reason about how you kind of step through the various axes one by one.
I know.
And that's because until now, our axes, we only had, the only way you could talk about axes was as integers, and they were left to right. And it was sort of up to you to think about this weird descending process and whatnot. But if we have these named axes, then you can just jump straight to the axis you care about to do a certain thing like a plot or whatever. So I think
so that would be good.
This whole thing could rehabilitate data set a little bit. I mean, it is very hard to use in some cases.
Okay, so question.
I mean, it seems though like these are two different things though. I mean, there's I think association arrays. Okay, I argue that there are probably association arrays that are more ragged, where you don't necessarily want to name all the levels like this.
What is an association array?
Oh, I mean, that's something that doesn't exist, but we were talking about a minute ago, which is just the issue of, consider this simple case, which is I've got 10,000 objects.
Yeah, right. As a way
to
store efficiently, column-oriented storage, basically.
Well, right, but it should be more general than column-oriented, right? Because I might have 3 levels of nested association, or nested associations of lists of associations, and so on. And if the keys are basically, if it's fundamentally, I mean, I guess maybe this has to do with it being not too ragged, but if fundamentally it is just a rectangular array of some kind, then you'd like to not have to repeat the keys a million times.
Right. So basically, it's an array, and then it's a key spec of some kind, where that array could be a numeric array, an efficiently packed numeric array, and so on. So it's similar to this named levels wrapper. It's a way to basically say how to index into this array. It isn't changing the array, but it's saying what the meaning of those different pieces of the array is and how you would index into it.
Yeah, exactly.
And
right,
arguably,
so it's naming of the elements, though, as opposed to naming of the levels. That's the distinction between these two.
Yes,
yes.
Right.
Well, quantity arrays is a different aspect of the same type of thing.
That's
I mean, I guess
another point.
This is something we talked about earlier. Or I mean, that there are a lot of different types of fundamentally array-like objects running around, and I mean, right now there's, I think, very little infrastructure for, if I want to implement an array-like object and I want to make sure that it works with flatten, it works with total, it works with, etc. That's kind of a pain right now, but that's maybe
let's
yet
call
another
this
discussion.
General concept, annotated arrays. Okay, how can they be annotated, right? Okay, so one annotation is what are the indices at a particular level, e.g. association keys. Another thing is what are the names of the levels. Another is what wrapper, e.g. quantity, is applied to each element.
But see, then there's other things, like there are more complicated cases. I mean, quantity array, geoposition, fine, but then there's also, I guess that gets a lot of the cases, but there's also things like sparse array and stuff like that.
Okay, so let's consider one more case here, which is...
Don't we also have a data array or something like that?
Yes. Okay, so then there's things like data array, geo array, which I don't think we quite have yet, but those are
I think those two, those two, so geoposition can be given a list of geopositions, and I think data array, I think those things are equivalent to quantity array, because fundamentally you could write it as just an array, a normal rectangular array with wrappers applied to each element.
Okay, right? But I claim there's a different thing, which is this is saying, and the same thing comes up in 3D graphics type stuff. This is saying what is the meaning of a particular index configuration, e.g. an actual, e.g. a geo grid of some kind, right? Where you're naming, so where you're trying to spend less effort, like in a geo-elevation data thing, where you're trying to say, rather than for every point saying this is its geoposition, you're merely giving, you're giving essentially an outer product of two, you're saying, okay, this is what the indices, and this is in a sense, what do the indices mean?
Right, which I'd argue is very analogous to quantity array, but yeah.
Is
Well,
it?
so what?
I thought quantity array is about values. Go ahead.
Wait, so maybe you're right. So maybe there are two sides to the annotation. So one side is whether you're annotating the keys, the indices, and just to keep in mind that if it's part of a bigger array, it might be that the annotation really just lives on one particular axis rather than on the whole array. Okay. So there's that kind of thing, and then there's an annotation on the values. Right. Exactly. And that would be something like with dates, it would be like, these are all in the following time zone, and I don't want to have to keep storing that. So that's an efficiency thing. And it might also it might even sometimes be a semantics thing that that it's possible to, like, I don't know.
You might want to do it as strings. You might want to have something which is a bunch of strings rather than having entity wrappers around them.
Yes.
Right. And about the quantity arrays, right? If all the quantities are commensurate, then maybe it's about values. But if one quantity is seconds and the other is meters, then you're implicitly imbuing it with different meanings. So it's a bit of a fuzzy line.
Okay, so I think I have worked on all these things, so I can explain. So quantity array uses Rob's framework, which it's currently called structured array framework, but it's a general array framework. It's very powerful, so it could do more things than just structured arrays. And so quantity array works that way. Data array is planned to work that way. Geoposition doesn't work that way because it preceded the structured framework. So we had geopositions of arrays before the structured array framework existed. So that's one aspect, and I fully agree that it will be very powerful to program things via that framework.
Sorry,
the second
is
thing
structured array
is
now called systematized array though? Or
sorry?
I just looked up the documentation. It said that structured array is no longer its name, and now it's
the thing here was that we decided to maintain them in the containers, in the resulting containers. We decided to keep the names of the types, quantity array, or in the future data array, because Steven complained multiple times that it was weird to have quantity arrays having the head structured array, and so we changed that to keep the head quantity array, which I think it's a good change.
Yeah, and so I mean, I'll just mention that another historical case that could be a structured array and probably really should have been is sparse array. It's so the idea of a structured array is that it represents some array, but it uses its own storage to do that.
Right.
So
I think that's a different thing. I think that's beyond. This is really dense, not very ragged arrays that we're talking about here. And there's a whole bunch of stuff that can be done for dense, not very ragged arrays.
Can I just ask though, for structured array, does it present a kind of API that we could use to prototype some of these ideas? Because one of the problems when it comes to prototyping is that there's some things you just can't implement with up values, right? There's a whole dispatch mechanism that we don't really have in the language to let you create your own arrays. Does structured array give us that?
Yes, structured array comes with an API for doing that, and it defines. So, it defines. It has an API which you have to fill in. You have to fill in certain things for functionality, and then when the functionality isn't there, it typically goes back to the normal array.
Is it documented, or is there an internal notebook that we could? Because I'm just
yes, I can send you the internal notebook, Tally.
Oh, fantastic! Thank you. Yeah, that's awesome. Thanks.
Okay, so unfortunately, I'm supposed to go to another outside meeting here. Although you guys could continue. This seems awfully productive. I mean, to me, this idea of an annotated array that allows you to, have a mapping for indices, levels, and values seems like a good concept. And then the question is, okay, so given that, we can then, many of these operations can refer to the, the mappings of indices and levels.
Well,
Right.
so much becomes, it also avoids us having to generalize various things that aren't fully general, because it's a lot of work to make total whatever, take a complex level spec. I don't know if that's one of the examples, but there are various things. Or flatten could, you could say 3,4 and flatten. Maybe it doesn't support that currently, but some of the use cases for that will just go away if we just support, an arbitrary index.
Right, but I mean,
it becomes
I think
less important.
the question really is, I'm still grappling with the idea of, I think Tally's analogy of, registers versus variables seems completely apt. But the story of that is levels now. We've understood how to do that for indices. That's what associations are doing.
So I have a comment there. So what you are calling named levels is what Einstein was calling indices 100 years ago. So these are well known.
Indeed. Yes.
And the problem there, they are not a perfect solution. They just solve some problems. They create some other problems. The problems they create is contractions. It's canonicalization. When you have TII minus TJJ, you have to realize that they mean the same thing. That's difficult. It's the same problem of lambda calculus.
And everything.
Yeah. That problem is solved with numbers. It's created by named indices.
Well, but maybe the way to think about it for us is if you've got two annotated arrays and their annotations are different. So this is a good question. If you've got two annotated arrays and you say annotated array of some array object, comma, let's say ij, and then you've got minus annotated array of array, the exact same array, ji, is that the zero array? And if it is the zero array, with what indices is it the zero array?
So that case will be transposed. That will be the first minus the transpose of the first.
Yeah, you've symmetrized it, I think.
Well, but is that what it means? But hold on, how do I know that? How do I know that? This is now matching up, because I thought this was just a local thing where these indices were just referring to how I was to reference. So in this case, right, imagine that my index, my part specification was this, that I were to say something like I goes to 4, I goes to this, j goes to 8. And that would get me the I equals 4, j equals 8 component.
Yeah, exactly.
Thing. Okay, or actually more to the point, I would probably want an association here.
Association there, yeah. And we might want to emphasize strings rather than random symbols, but symbols seem fine too.
Yeah, okay. But so then this is the way that you would extract that part. Now the question is the ij thing and the ji thing, are they actually different? Or is that merely an index? Is it the case that these two things, if the raw content of this array is the same, boy.
No. This is actually very well defined. So just there's an identity here, which is annotated array. Because what you've got to ask is, how does it act? Like when you look up things, what will you get? That's how you think about these things. And swapping the list, reversing the list there, for the second argument of annotated array is the same as transposing the first argument. At least with respect to,
okay, so the claim is that this is equivalent to, for ij, this is equivalent to part 4, 8, right? But whereas if I were to do this, to have ji there, then this is equivalent, then that will be equivalent to part 8, 4.
Right. So when you form that sum, or that subtraction, you're going to end up with another annotated array. I'm not sure what choice of order it should have for the ji there, but we do know how it acts. So There is
But
flexibility
wait,
behind
I'm
the
sorry.
scenes.
I have to. Sorry, I have to interrupt you. What are I and j? Because this looks right. I thought the point of the annotated array is that we're naming our levels. But if I and j are just I and j, what have we accomplished?
So
Naming
I is
the
the
level.
first.
Yeah.
Yeah. Those are the names.
So
Right.
And
what
they
we
just
could
appear
do
in order.
is we
Okay.
could say,
So where's 4 and 8? I is going to 1 and j is going to 2. And in the second one, j is going to 1 and I is going to 2.
that's right. So what's
And you're somehow suggesting that that plus somehow dig in and start
where's the
renaming
plus?
things?
Where's the plus? What's the plus? Where's the? Are you talking about this case here?
Yes.
Okay, I don't understand that case here yet. That's my point. I don't understand that case. That is, to me, I think this is the answer to this is 0.
No.
No, it's not.
No. This is what I showed a couple of weeks ago in Exact. What Exact would do there is simply producing a new single annotated array, which is array minus transpose of array, comma ij.
Mm-hmm.
Yes,
this is
correct.
what is done everywhere.
Yeah. No, Stephen, so that's well defined.
But then these are indices. They're not named levels.
These are indices, right? Which I think is what named levels means. Like
well,
in
I'm
index.
not sure that they're the same thing. By the way, we had a bunch of comments on our live stream that are interesting. I unfortunately really have to go to this outside meeting. Could I leave you guys to continue this for a bit? I think you're productive, probably more productive without me. So can we go ahead and do that? Here, you can.
Sure.
Who can pick up? Who has access to these files? Devin, you have access to these files, right?
Yeah.
Okay. So I just have to drop out here. And I encourage you to look at some of these comments on the live stream. They're kind of interesting. And various comments about how this should work on GPUs. Yeah, we agree. All right, I unfortunately have to go, but please continue. And I look forward to hearing what happened here. All right, I'm unsure.